For centuries, Venus has been a planet of intrigue and mystery. Known as Earth's twin, it shines in our night sky, yet remains one of the most hostile places in our solar system. Back in 2021, the Bepi-Colombo mission, a joint project by the European Space Agency and Japan Aerospace Exploration Agency, made a fleeting visit to Venus. However, it was in April of this year that a reanalysis of the data revealed unexpected findings. There were oxygen and carbon ions leaking from the planet's upper atmosphere. These heavy ions, which are normally slow and difficult to move, were found accelerating at unexpected speeds. Scientists still can't figure out what the forces are behind this phenomenon. Is it an electrostatic wind, or perhaps centrifugal processes have intervened? Venus has long been an object of exploration. Early missions such as Mariner 2 confirmed the absence of a magnetic field, and Venera 4 gave us our first glimpse of its thick, toxic atmosphere. Pioneer Venus Orbiter and Venus Express mapped previously unknown regions, but many questions remain. So how did Bepi-Colombo allow a more detailed picture to emerge? How did Venus lose its water? And why is its atmosphere so different from Earth's? And most importantly, could we survive on Venus? Today, we learn about the harsh realities and tantalizing possibilities of setting up a home with our mysterious neighbor. Venus's atmosphere is a complex and fascinating study. Composed mostly of carbon dioxide and sulfuric acid clouds, it starkly contrasts to the life-sustaining air we breathe on Earth. At Venus's surface, the pressure is 90 times Earth's pressure, and temperatures reach 869 degrees Fahrenheit. This incredible heat is the result of the greenhouse effect, trapping solar energy in the dense, opaque atmosphere. Our understanding of this hostile environment began with early missions such as Mariner 2, which first confirmed extreme surface temperatures. The Venera 4 spacecraft made deep measurements, revealing a dense carbon dioxide atmosphere and the presence of sulfuric acid clouds. The Pioneer Venus Orbiter mapped the upper atmosphere, showing the dynamism of Venus's weather systems and the presence of thunderstorms. Then came Bepi-Colombo. During flybys, the spacecraft penetrated previously unexplored regions of Venus's magnetosphere. Its instruments detected positively charged oxygen and carbon ions being carried away from the upper atmosphere. These findings were unprecedented because heavy ions like these are usually slow-moving and difficult to dislodge. The output of these ions testifies to the complex interaction between the solar wind and the atmosphere on Venus. Unlike the Earth, which has a strong intrinsic magnetic field, Venus has only a weak-induced magnetosphere created by the interaction of the solar wind with its atmosphere. This makes Venus more susceptible to atmospheric destruction by solar particles. Now, for the most startling fact, a comparative study of water loss by Earth and Venus was conducted. Both planets, according to scientists, started with the same amount of water. However, Venus's proximity to the Sun and its lack of a protective magnetic field allowed solar radiation to break down the water molecules in its atmosphere. Hydrogen, being the lighter element, escaped into space, while oxygen remained, contributing to the dense carbon dioxide atmosphere we see today on Venus. By contrast, Earth's strong magnetic field has protected its atmosphere, preventing significant water loss and enabling the development of life. The striking difference emphasizes the importance of magnetic fields for planetary habitability. Understanding the atmospheric mysteries of Venus not only provides a glimpse into its past, but also serves as a kind of precautionary measure for us on Earth. Okay, a bit of history for context. Space missions have been the cornerstone of our understanding of Venus. Each mission, with its unique capabilities, has contributed to unraveling the planet's mysterious environment. The journey began with Mariner 2 in 1962, the first successful mission to another planet. Mariner 2 confirmed the extreme surface temperatures of Venus and established the absence of its own magnetic field, setting the stage for future explorations. In 1967, the Soviet probe Venera 4 made the first direct measurements of Venus's atmosphere. It detected a dense carbon dioxide atmosphere with clouds of sulfuric acid and provided us with the first data on the ionosphere. The Pioneer Venus orbiter, launched in 1978, began systematically mapping different regions of Venus's atmosphere, providing extensive data on its composition and dynamics. It confirmed the presence of heavy ion streams and helped identify the bow shock and magnetosheath formed by the interaction of the solar wind with Venus's atmosphere. The Venus Express mission, launched in 2006, built on these results and used the space plasma and energetic atoms analyzer to study ion emissions in detail. It measured the absolute number of hydrogen, helium, and oxygen ions escaping, providing important insights into atmospheric loss processes. In August 2021, Bepi Colombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, made its second flyby of Venus. This spacecraft penetrated previously unexplored regions of Venus's induced magnetosphere. The mass spectral analyzer and ion analyzer detected cold oxygen and carbon ions escaping from the atmosphere. These ions were detected at a distance of about 6 planetary radii in a previously unexplored region. Among the departing ions were O-positive and C-positive, the latter being the first to be seen escaping from Venus's atmosphere. This indicates a complex interaction between the solar wind and the induced magnetosphere of Venus. Unlike Earth, which has a strong magnetic field of its own, Venus has only an induced magnetosphere, formed by the interaction of the solar wind with its atmosphere. The induced magnetic field is comet-shaped, creating a magnetosphere in which solar wind particles are slowed down and heated. Bepi Colombo's observations of the ion ejection mechanisms in this region have provided new insights into the processes that are inexorably destroying Venus's atmosphere. Understanding these mechanisms is critical to understanding the evolution of Venus's atmosphere, in particular the process of losing its initial water concentration. The quest to understand Venus involves not only studying its hostile environment, but also looking for the potential of life in the most unexpected places. Even in Venus's harsh atmosphere, scientists are searching for the fundamental components of life. High-tech experiments aim to study Venus's atmosphere in search of evidence of life-supporting molecules. The discovery of phosphine gas in the upper atmosphere of Venus in 2020 has sparked intense interest. On Earth, phosphine is associated with biological processes, leading scientists to wonder whether similar processes could occur on Venus. However, the harsh conditions on Venus complicate this search because of the extremely high surface temperatures and immense atmospheric pressure. Any potential life forms must be incredibly robust and resilient. Despite these challenges, the search continues. NASA's upcoming missions, Da Vinci and Veritas, aim to delve deeper into the atmosphere and surface of Venus. The Da Vinci mission will focus on measuring atmospheric gases, including the presence of any of the so-called noble gases and other elements, from the top of the atmosphere to the surface. These data will help scientists build new climate models and study the chemical composition of the atmosphere in more detail. The Da Vinci lander will provide unprecedented insight into the composition of the atmosphere and possibly detect molecules that may be precursors to life. These measurements will be critical to understanding the habitability potential of Venus and other similar exoplanets. The Veritas mission, on the other hand, will create high-resolution maps of Venus's surface. By studying the planet's geology and topography, scientists hope to discover signs of past volcanic activity and water flows, which would be important clues to understanding Venus's history and its potential to sustain life. This detailed study of Venus's surface and atmosphere helps astrobiologists improve their models of planetary habitability. Venus provides an instructive example. Despite its similarities to Earth, its environment has taken a radically different path. Understanding these divergent evolutionary paths may help us in our search for habitable worlds beyond our solar system. Venus and Earth, often referred to as sister planets, have striking similarities in size, mass, and composition. However, their environmental and atmospheric conditions could not be more different. Venus's atmosphere consists mainly of carbon dioxide and nitrogen, with clouds of sulfuric acid, creating a dense, toxic blanket. Earth's atmosphere, in contrast, is composed mainly of nitrogen and oxygen, supporting a variety of life forms. Atmospheric pressure on Venus is about 90 times higher than Earth's, which is approximately equivalent to being underwater at a depth of 3,000 feet or 900 meters. The greenhouse effect is extreme here. Solar radiation penetrates through dense clouds, heating the surface, but a dense atmosphere of carbon dioxide traps this heat, resulting in a surface temperature of about 869 degrees Fahrenheit, 465 degrees Celsius. On Earth, on the other hand, the greenhouse effect is in a delicate balance that maintains temperatures suitable for life. There are also several fundamental differences between the two planets, in addition to their proximity to the Sun. Earth has a relatively fast rotation period of 24 hours and a stable axial tilt, which promotes even heat distribution and supports seasonal changes. Venus, on the other hand, rotates slowly and in the opposite direction of most planets in the solar system. It has a rotation period of 243 Earth days. This slow rotation and lack of significant axial tilt results in minimal temperature fluctuations between day and night. The slow retrograde rotation contributes to Venus's extreme weather patterns and thick, super-rotating cloud layers that circle the planet every 4 Earth days. These clouds reflect a significant amount of sunlight, giving Venus a bright appearance, but also trapping a tremendous amount of heat. Geologically, both planets have volcanic landscapes. But whereas on Earth tectonic activity recycles carbon and supports a diverse climate, the surface of Venus is dominated by vast volcanic plains and high-altitude regions. The lack of tectonic plates on Venus means that heat is stored beneath the crust until it's released by catastrophic volcanic events, reshaping vast areas of the planet. The presence and loss of water are crucial factors in the different evolutionary paths of these planets. Measurements of the ratio of deuterium to hydrogen in Venus's atmosphere indicate that the planet once had a significant amount of water. The high ratio suggests that the lighter hydrogen was lost over time, while the heavier deuterium remained, indicating an historical loss of water. The different evolutionary paths of Venus and Earth give rise to the realization that the planet may be habitable. Venus's proximity to the Sun probably created a greenhouse effect that vaporized all the oceans and led to its current inhospitable state. Earth, which is at a moderate distance from the Sun and has a protective magnetic field, has retained liquid water and a stable climate favorable to life. As we enter a new era of space exploration, several ambitious missions are about to reveal more of its secrets. The European Space Agency's Envision mission, scheduled for launch in 2031, is designed to provide a comprehensive understanding of Venus from its core to its outer atmosphere. Envision will build on the discoveries of previous missions, such as Venus Express, which have hinted at volcanic activity and will offer a detailed understanding of Venus's geological and atmospheric processes. Envision will carry an extensive suite of instruments designed for a comprehensive study of the planet. Synthetic aperture radar will map the surface at resolutions of up to 10 meters, revealing details about surface texture and geological activity. Its subsurface radar sounder will penetrate up to a mile below the surface, searching for underground structures and layers. 3 spectrometers, VenSpec-U, VenSpec-H, and VenSpec-M, will analyze trace gases and look for volcanic gas plumes and map surface composition. The gravity radiological experiment will use radio waves to study the planet's internal structure and atmospheric properties. Envision will help unravel how geologic processes, such as volcanism and tectonics, affect the planet's atmosphere and climate. This integrated approach will provide clinical data to answer long-standing questions about Venus's past and present geologic activity and the dynamism of its atmosphere. India's Chakrayan mission, led by the Indian Space Research Organization, is another important addition to the exploration of the planet. Planned for launch in the early 2030s, the probe will study the atmosphere and surface of Venus using a suite of advanced instruments. Instruments will be installed on board to analyze cloud layers, atmospheric composition, and features of the planet's surface. Using infrared and ultraviolet cameras, the spacecraft will study the dynamics of Venus's dense cloud cover and the interaction of the atmosphere with the surface. One of Chakrayan's main goals is to understand the sulfur cycle on Venus, which plays a crucial role in the chemistry of its atmosphere. By studying the distribution of sulfur compounds and their interactions with other elements, the Chakrayan mission will contribute to our understanding of the complex atmospheric processes on this yellow planet. These missions have potential to revolutionize our understanding of Venus. By combining data from Envision, Chakrayan, Da Vinci, and Veritas, scientists will have a complete picture of the geologic and atmospheric evolution of Venus. These missions will provide crucial data on volcanic and tectonic activity, atmospheric composition, and surface interactions, helping to build a detailed picture of the planet's past, present, and even its future. Data from these missions will also help us understand planetary habitability and the conditions necessary for life. By studying Venus, we'll be able to improve models of atmospheric and geologic processes, which will improve our ability to identify habitable environments on exoplanets. Looking to the future, the ultimate goal of Venus's exploration is to pave the way for future human missions. Although the planet's extreme conditions pose significant challenges, advances in technology and a better understanding of the environment may one day make planetary exploration possible. Future missions could include robotic explorers capable of withstanding the harsh conditions of Venus's surface and then develop habitats that would protect humans from the intense heat and pressure. These habitats would then be equipped with advanced life support systems, allowing for longer stays on the planet and more in-depth scientific research. Exploring Venus is not just about exploring our nearest neighboring planet. It's also about pushing the boundaries of what's possible in space exploration. By overcoming the challenges of Venus, we'll be able to develop the technologies and strategies that will be needed to explore other extreme environments in our solar system and beyond. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the Moon, Io. Unlike any other orbiting the mighty Jupiter, shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close approach is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles, given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomena in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main-sequence star slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shock wave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The discovery of the Boat GRB, also referred to as the brightest of all time, in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. Boat was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of such cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of a gamma-ray burst. The Boat GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While Boat GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days, and the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shock waves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, While some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Among the thousands of lifeless planets, it's impossible to find one as picturesque and alive as the Earth, which seems to violate the very laws of the cosmos. All life that has ever appeared on this planet owes its existence to water. The first complex molecules, the first organisms, the first humans, all of them have their roots in water. But how did so much liquid water appear on Earth, among desert planets? For all of science, the place of origin of water remains a mystery. Whether water originated in the hellish bowels of the young Earth or millions of light years away in inaccessible depths of space is a confusing question for all scientists. But the closer we get to the solution, the closer we will get to answering the question, are we alone? Today, we'll try to find the sources of water and life on our planet, diving into the very beginning of the solar system and find out why water chose the Earth, saving it from the fate of Mars and Venus. Approximately 70% of the Earth's surface is covered by water. The imposing number of bodies of water on the planet seem to us to be something quite ordinary, and based on what we know about the birth of planets, the Earth should have been completely dry. Let's go back to the very beginning of the life of our solar system. We're looking at a young sun, which has just formed from the remnants of an ancient supernova, which left a giant plume around it, a protoplanetary disk of dust and gas that spread over hundreds of millions of kilometers due to nuclear processes in the star. Many of the planets we know today, including the Earth, will be formed from these building blocks in billions of years. Since the only materials that could exist around the Sun at that time were stone and iron, the four nearest planets were formed from them. According to a recent study by the California Institute of Technology, the planetesimals from which the Earth was formed consisted of dry, stony materials. These building materials did not contain volatile substances such as water. In particular, gas was unavailable in the early stages because it was mostly ejected beyond the orbit of Mars, so an atmosphere was out of the question. But wait, what does the atmosphere have to do with it? In the early days, the Earth did not have a moderate temperature as it does now. The disk was very hot, and the Sun was very active, which is why instead of water, seas of magma were pouring out on the planet under deadly UV radiation. Therefore, there was no way that water could be retained on such a hot Earth in liquid form. And because there was no atmosphere, water could not accumulate as steam. The magmatic period could have lasted for several tens of millions of years until the surface cooled down. And, according to many studies, including those of the University of Chicago, water began to appear after that. But how did that happen? The Earth couldn't have formed with an ocean because it would have boiled over due to the hot protoplanetary disk. It would have become a scorched, dry planet like Venus, for example. Instead, water spilled into its interior, which created the conditions for the emergence of all life that exists today. So how could water get to the dry Earth? Perhaps the answer to this mysterious question is right above us. Water could have been brought to Earth by extraterrestrial messengers traveling through space. No, we're not talking about alien life forms, but ordinary comets and asteroids. In a groundbreaking study conducted by scientists using NASA's Stratospheric Observatory for Infrared Astronomy, Sophia. Water was first detected on the surface of the asteroid Bennu. The presence of water molecules in the rocks of Bennu indicates that such asteroids could have delivered water to Earth in the early days of the solar system. The discovery was made possible thanks to Sophia's unique capabilities, which include a powerful telescope mounted on a Boeing 747 SP aircraft. By flying over 99% of the Earth's atmospheric water vapor, Sophia was able to capture infrared waves that are otherwise blocked, allowing for precise observations of the composition of Bennu's surface. Comets are composed of frozen gases of rocks and dust and orbit the Sun in highly deformed elliptical orbits. They're actually snow comets that carry a lot of water and other building materials, such as methane, ammonia, and carbon dioxide. As they approach the Sun, comets melt, releasing clouds of water vapor that are captured by the Earth's gravity. Asteroids are the remnants of the primordial solar system during its active formation. They also had a significant impact on filling the Earth with various important elements, such as silicate rocks, iron, nickel, etc., depending on the class of composition. For example, the most common chondritic asteroids, or Class C, have up to 13.5% water in their composition, the molecules of which could be transported as space dust. Therefore, it seems very likely that comets and asteroids may be behind the global appearance of water on Earth. The carbonaceous asteroid Bennu is considered to be a time capsule from the early solar system, containing valuable clues about its formation and evolution. The discovery of water on Bennu adds to the growing body of evidence that carbonaceous asteroids may be important sources of water and organic compounds essential for life. The presence of hydrated materials on Bennu, which form in the presence of water, suggests that Bennu's parent body had liquid water in the past. This also means that Bennu, or similar asteroids, could have been water carriers to the early Earth, contributing to the formation of the planet's initial water supply. In particular, in the period from 3.8 to 4.1 billion years ago, the inner planets of the solar system experienced a strong bombardment by asteroids and comets, better known as the Late Heavy Bombardment. This event may explain the abundance of water on the planet, but it still requires in-depth research, such as the craters on the Moon, which were probably left by the bombardment. The atmosphere also did not stand in the way of these travelers, so asteroids and comets freely entered the Earth's space, accumulating the first water. According to the research of space chemists led by Nicolas Dauphaz, about 10% of water could have been brought to Earth by comets and asteroids. Along with asteroids and comets, meteorites are another candidate. Meteorites are fragments of asteroids or comets. The most likely source of water could be molten meteorites, which have been floating around since the formation of the solar system. However, recent studies of this type of meteorite have shown that they have a very low water content. But all is not lost for meteorites. There are several other types, including carbonation chondrites and enstatite chondrites. Despite their complicated names, these two species are currently considered to be the most likely source of water on Earth, as they contain up to 20% water on average and could even bring 3 times as much water to Earth as our oceans have now. Over time, as the Earth cooled and geologic activity decreased, it took the first steps toward the developing plate tectonics. The movement of these plates formed new mountains and ocean trenches, contributing to the system of water transfer from rivers to oceans. Plate tectonics also allowed water to be stored in the Earth's evolving mantle, motivating geologic activity and thus the formation of water within the planet. Constant bombardment by cosmic bodies also continued to fill the Earth with water. Thus, water arrived on the Earth almost continuously, gradually covering its revitalized surface with water. The still young Earth, which was just beginning its active internal formation approximately between 2.5 and 4 billion years ago, did not have sufficient opportunities to drain water into, for example, the mantle, due to its limited capacity. Therefore, the combined efforts of asteroids, comets, and internal activity could have completely covered our Earth with water, making it a complete water world without a hint of land. In 2021, scientists from Harvard University, led by Junji Dong, conducted a geochemical study of the planet's water reserves. To their surprise, it turned out that the Earth's original ocean could have been 1 to 2 times larger than it is now. According to Junji Dong, this ocean could have flooded 70 to 90% of the early continents. A group of scientists calculated and compared the approximate amount of water in the mantle today and billions of years ago, and found that the ancient mantle could not hold as much water as it does now. This means that residual water would have to be stored on the Earth's surface. This theory can change our entire understanding of how the ancient Earth developed and, in particular, all life. Currently, theories about the origin of living organisms in shallow ponds with a mixture of different minerals and building blocks on land or in hydrothermal substances at the bottom of the ocean are popular. However, the global ocean may upend these assumptions, requiring new explanations of how life came to be or a revision of what we know about the conditions for its formation. For example, scientists are already putting forward the first theories about where organisms evolved. Thomas Carroll believes that protected water pockets in oceanic rocks may be the answer to this question. Yet, if the Earth had remained a water world, the continents and life forms we know would never have formed. The delicate balance between the water brought by asteroids and comets and the Earth's tectonics has made the planet ideal for habitation. And if there was too much water, or too little, Junji Dong says, nothing would work. But only extraterrestrial space bodies could not form and maintain an ocean for a long time. Venus and Mars also experienced bombardment, but they failed to retain much water on their surfaces for a long list of reasons. And one of these reasons is the location and temperature regime in the solar system. As long as Venus is too close to the Sun and Mars is too far away, the Earth seems to be in an ideal place to maintain water in liquid rather than gaseous or solid forms. Such a place in planetary systems is called the Goldilocks zone. This zone, which is most suitable for the emergence of life, differs in each system depending on the type of star. For us, it exists between 0.99 AU and 1.7 AU, right on the edge of the zone. Without the Goldilocks zone, the water that comes to us through external pathways would evaporate or turn into ice. Moreover, the ideal zone maintains the water cycle, regulating weather and climate, and balances the functioning of ecosystems. The Goldilocks zone played an equally important role in the formation of the Earth as a habitable planet, supporting and storing water and all the additional elements brought from outside and formed within the Earth itself. All of the above theories and assumptions require careful and serious research to finally establish the full story of water's origin. The recent discovery of Bennu emphasizes the importance of ongoing research to understand the origin of water on Earth. Such research not only supports existing theories, but also provides new knowledge and evidence, deepening our knowledge of the early solar system and potential sources of water. Missions such as OSIRIS-REx, which collected samples from the surface of Bennu, aim to return these samples to Earth for detailed laboratory analysis. These samples will provide unprecedented information about the mineralogical and chemical properties of Bennu, further illuminating its role in the history of the solar system. But in fact, researching this issue is by no means an easy task. First of all, the water that scientists are most interested in is hidden deep underground under the oceans. The water is likely to have a different composition than seawater, so it would be possible to find out exactly what the main sources of water were. Therefore, scientists are probably currently using the wrong DH, deuterium to hydrogen ratio, for the Earth, which is the main method of comparing the chemical composition of the Earth and other cosmic bodies. However, it's still extremely difficult to get to the mantle. Although scientists have already had some success in this direction, having drilled a mile under the floor of the Atlantic Ocean for the first time, where they retrieved the first pieces of the mantle. But full-fledged and high-quality water studies are still far from being conducted there. Despite this, the difficulty is further complicated by the insufficient sample of comets and asteroids to study the correlation between their chemical composition and water bodies on Earth. The protoplanetary disk around the Sun, as it moves away from it, has a completely different ratio of deuterium to hydrogen in its composition. Therefore, it's difficult to determine where the space body that brought the water could have formed in order to better understand its composition and amount of water. In addition, the diversity of water sources requires a multifaceted study to determine the contribution of each group of objects. To solve this problem, it's only necessary to study several space bodies at different distances to determine which population of space bodies is responsible for water on the planet. But today scientists can only measure the closest and brightest objects. The water on Earth itself can also confuse the trail due to changes in its composition over millions of years. The search for what filled the Earth with water will take a long time, but gradual improvements in analytical methods and future research missions will one day shed light on the sources of our life, including our own. Scientists continue to work in the hope of advancing our understanding of how water got into the solar system. In 2021, cosmochemist Laurette Piani from the University of Lorraine analyzed a very rare type of meteorite called enstatite chondrite. The isotropic composition of this meteorite is similar to that of the Earth, and it's likely to be a remnant of planetary material from the outer solar system. According to the study, these meteorites could have brought 3 times as much water to Earth as our oceans have now. Moreover, the isotopes of hydrogen and nitrogen on enstatite chondrites match those found in the mantle, which also indicates that most of the atmospheric air could have come from these rocks. However, the composition of seawater does not quite match that of meteorite water. It is possible that other space bodies could have mixed with the water, changing its original chemical content and confusing scientists. On the other hand, a group of scientists led by Edward D. Young put together a completely unexpected theory that could move space objects from the first place in the group of the main sources of water on Earth. Most of the water could have appeared on the planet from former magma oceans, where oxygen interacted with hydrogen in the early atmosphere. The interaction of magma and hydrogen produces water. This amazing process does not negate the impact of asteroids, comets, and meteorites, but rather adds to the history of water on Earth. Finally, in June 2023, another stunning theory emerged that goes against what we know about the formation of the Earth. According to this theory, instead of water appearing on Earth due to cosmic bodies, our planet was attracted mostly by pebbles and ice particles from the protoplanetary disk in the early stages of its existence, like a vacuum cleaner. Thus, the presence of water doesn't depend on a random event like comet bombardment, according to lead author Isaac Agnet, and therefore the Earth could have formed in as little as 3 million years instead of hundreds of millions of years. This theory could overturn all knowledge about the formation of planetary systems and the origin of water in particular, so it needs a lot more careful research to make its mark even louder. The history of water on Earth is one of the most intriguing questions for modern science. Scientists propose many theories and assumptions based on studies of samples as old as the Sun itself, getting closer to the desired solution every day. Whether brought by comets, meteorites, and asteroids, or formed by the Earth itself, water is fascinating for its mystery and ability to shelter and sustain life. And one day, its mastery will be tamed, and we will finally know how the Earth came to life. Imagine a line, a simple, unbroken line stretching into infinity. This line, in its purest form, represents the first dimension, a realm of length but without depth, a universe infinitely long but impossibly thin. Now, let's broaden our perspective. Introduce a second line intersecting the first. and suddenly we're in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable alien to them. As we go one step higher, we find ourselves in the familiar embrace of the third dimension. This is where depth comes in, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe takes on texture and shape. But what if we could add another layer? Time is the elusive fourth dimension that permeates our three-dimensional space. Invisible but omnipresent, it dictates the rhythm of our lives, a continuous thread connecting each previous moment with the current one, and the current one with the next. In this realm, our understanding of reality becomes more complex and broader. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our sensory perception. However, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces that govern the universe. These higher dimensions, although beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us as we try to unravel their mysteries together today, one dimension at a time. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. Philosophers once pondered the nature of existence, laying the foundations for our understanding of space. In their discussions, they questioned the very essence of reality, imagining realms beyond the tangible. As the centuries passed, these philosophical speculations paved the way for more structured inquiry into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions that form the fabric of space-time. Albert Einstein, in turn, based on the foundation laid by Minkowski, presented the revolutionary theory of general relativity, restructuring our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical quest of the ancient thinkers to the scientific revolutions sparked by Minkowski and Einstein, the journey through the evolution of spatial thinking reveals a relentless quest to comprehend the true nature of our universe. So, over time, we've come to realize that to truly comprehend the fabric of our reality, we must go beyond the three tangible dimensions into the realm of the fourth dimension, time. The concept of time as a dimension is both profound and persuasive, defining our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It moves inexorably forward, from the past through the present and into the future. This unidirectional flow of time distinguishes it from space, bringing to the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, consider a simple everyday scenario: organizing a meeting. When we suggest that someone meet at a certain place, we unconsciously navigate the three basic spatial dimensions to determine where. It makes sense that if we arrived at different places, no meeting would take place. However, the when, the dimension without which the meeting will not take place, is no less important. That is, coming with your friend to the same place but at different time intervals, you'll not be able to see each other. This intertwining of space and time is manifested in the concept of world line, the path that an object or person takes through space-time, thus representing its history and future. The idea of world lines provides a vivid illustration of how events are linked together in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not just a spatial coordinate, but a space-time coordinate, the only point in the vast continuum of the universe where both where and when coincide. This principle applies not only to simple encounters but also to the fundamental workings of the cosmos. Celestial bodies from planets to stars trace their own world lines through space-time, their paths determined by the interplay of spatial positions and temporal moments. For example, the Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space to the dynamic unfolding of events. Time allows us to understand the universe not as a set of individual moments, but as a continuous narrative where cause and effect bind our reality into a coherent whole. The inclusion of time as a dimension has catalyzed major advances in physics, particularly through Einstein's theories of relativity, which we've already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, it slows down or shrinks depending on the velocity of an object, challenged the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different reference frames. This phenomenon is confirmed by experiments, for example, with atomic clocks on fast-moving airplanes. In quantum mechanics, time as a dimension underlies the evolution of particle state governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, where the time dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm where our everyday experience and the laws of physics as we know them are fundamentally challenged and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not just speculative constructs, but important components in the quest for a deeper understanding of the universe. In theories such as string theory, these higher dimensions offer solutions to some of physics' most challenging mysteries, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions is that our perception is inherently three-dimensional. Therefore, analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called a flatlander, living in a flat two-dimensional world. This being can move forward and backward, left and right, but has no concept of moving up and down because these dimensions do not exist in its two-dimensional experience. Imagine a three-dimensional sphere passing through this two-dimensional world. To a flatlander, the sphere would first appear as a dot when the sphere is just touching the two-dimensional plane, gradually increasing into a circle as more of the sphere passes through the plane, and then decreasing again to a point as the sphere leaves the plane, before disappearing altogether. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears, without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, posits that particles are not the individual points we see them to be, but tiny vibrating strings, whose modes of vibration determine the properties of the particles. This theory requires the existence of more than 4 known dimensions. In fact, it suggests that there may be as many as 10 or 11. These additional dimensions are compacted or convolved so that they are imperceptible on our scale, like the sphere in the flatlander example. In the fifth dimension, we encounter a space containing all possible universes that start from the same initial conditions as our own universe. Imagine a tree, each branch representing a different decision or outcome leading to a different reality, all coming from the same trunk. Just as a person standing at the base of the tree can choose which branch to climb, a being with access to the fifth dimension can explore these alternate realities, each a variation of our own universe, but with slightly different outcomes. The ascent to the sixth dimension opens a plane containing all possible universes with the same initial conditions as ours, but with any possible set of laws of physics. If we think of each universe as a sheet of paper, the sixth dimension would be like a stack of such sheets, each representing a different universe. A being capable of traveling through the sixth dimension could hop between these universes, learning the different outcomes and laws governing each reality. The seventh dimension extends this concept to include universes that start from different initial conditions. To use a library analogy, each book represents a different universe. The seventh dimension encompasses the entire library, offering not just different stories, universes with the same initial conditions as ours but with different outcomes, but completely different genres, universes with different initial conditions. A seven-dimensional being could move through this library, experiencing an infinite number of universes, each with its own unique initial conditions and physical laws. In the eighth dimension, we find a web of all possible universes, each with its own initial conditions and laws of physics, as well as all possible variants of their development in time. Imagine a huge web where each thread represents the timeline of a separate universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The eighth dimension encompasses this entire web, allowing you to travel between any nodes, exploring the connections between different universes and their history. As we approach the ninth dimension, we encounter all possible laws of physics and initial conditions that have existed or will ever exist. This dimension can be compared to the art of origami, where a single piece of paper can be folded into numerous shapes. Each fold represents a change in the initial conditions or laws of the universe. And the ninth dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being living in the ninth dimension will not just have absolute freedom to cross the boundaries between all possible realms of reality, it will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It's the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline, and all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is challenging because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within that universe. Moving from trunk to leaves, we move from the initial conditions of the universe, lower dimensions, through the various choices and events, higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point where all these possibilities come together, the singularity of infinite potential outcomes. It suggests a cosmos in which all possible outcomes not only can happen, but happen in some timeline or universe in the 10th dimension. The concept itself invites us to reflect on the vastness of possibilities that lie beyond our observable universe. It raises questions about fate, choice, and the underlying structure of the cosmos, prompting a broader exploration of potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and fourth-dimensional time has profound implications for both physics and cosmology. Not only is this field of study designed to challenge our fundamental understanding of the universe, but it may also hold the key to uniting the disparate forces of nature, potentially solving some of cosmology's most enigmatic puzzles. Recognizing the existence of higher dimensions plays a key role in the search for a theory of everything, a single framework that will seamlessly unify general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the intricate world of subatomic particles. Higher dimensions may also offer new insights into cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter may be gravitational effects from matter in parallel branches, a concept from M-theory, which suggests multiple parallel membranes, or branes, as fundamental components of the universe, each potentially containing another universe in higher dimensions. Looking to the future in the field of energy, mastering the intricacies of higher dimensions could pave the way to harness forms and mechanisms of energy that we cannot now even imagine, and potentially lead to the creation of clean, virtually inexhaustible sources of energy. Similarly, the field of space travel could be revolutionized by a better understanding of the fabric of space-time, perhaps eventually enabling warp drives or other forms of faster-than-light travel, concepts that are currently in the realm of science fiction but could be theoretically plausible within higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle gas pedals such as the Large Hadron Collider at CERN, looking for evidence of additional dimensions and the particles that may inhabit them. This experimental work is complemented by theoretical studies that delve physicists and mathematicians into the abstract realms of high-dimensional spaces. As we complete our journey through the dimensions, from the simplicity of a line extending into infinity to the unfathomable complexity of the 10th dimension, we're faced with the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through math, we can describe properties and relationships within higher dimensions, and physics offers theories such as string theory and M-theory that hint at the existence of these additional dimensions. Animation such as tesseracts allows us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe. Just as the transition from a flat Earth to a spherical Earth many centuries ago broadened humanity's horizons, this expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place in it. Have you ever heard of a galaxy that defies categorization? Imagine a cosmic structure that combines an ancient dormant core surrounded by a bright halo of young stars. This is not your typical spiral or elliptical galaxy, but something much more mysterious. A Hoag object. Initially mistaken for a planetary nebula or gravitational lens, the true nature of Hoag's object remained hidden until more advanced observations revealed its unique structure. The central elliptical core appears red and inactive, while the outer ring is bright blue, teeming with new star formation. A clear gap separates the two components as if they belong to different galaxies. The object spans an impressive 121,000 light-years wide, with a central core about 17,000 light-years across and an outer ring stretching out 75,000 light-years. This apparent gap between the core and the ring is wider than the ring itself, which is a surprising feature for such a colossal galaxy. Ring galaxies, like Hoag's object, are extremely rare, making up less than 0.1% of all known galaxies. They often arise from complex cosmic events, but Hoag's object seems to maintain a calm and orderly appearance, which further deepens the mystery. Despite decades of research, astronomers are still grappling with the question of the origin of this galaxy. Was it the result of a quiet accretion process, or did a cosmic collision play a role? Arthur Hoag, a prominent astronomer of the mid-20th century, made a discovery that would intrigue and puzzle scientists for decades to come. In 1950, while conducting a study of the night sky, the astronomer came across a celestial object that defied conventional classification. This object, later named after him, had characteristics unlike any previously observed galaxy. At first glance, Hoag's object appeared to be a planetary nebula, a cloud of gas and dust surrounding a dying star. However, its unusual structure, consisting of a central core surrounded by a luminous ring, suggested otherwise. Early images taken by the astronomer's telescope showed a clear separation between the inner and outer components, prompting curiosity and speculation. Initial hypotheses varied widely. Hoag himself hypothesized that it could be a planetary nebula, or even a gravitational lens. The gravitational lens hypothesis suggested that the object was not a galaxy at all, but rather a massive elliptical galaxy magnifying a background galaxy in a ring-like shape. Gravitational lenses occur when a massive object, such as an elliptical galaxy, bends the light of a more distant object behind it. This bending creates a ring of light around the foreground object, known as the Einstein ring. In early observations, the outer ring of Hoag's object resembled such a lens, suggesting that it may be a foreground galaxy amplifying the light of a more distant object. For nearly 4 decades, the true nature of the Hoag object remained uncertain. It was not until 1987 that astronomers equipped with better technology were able to confirm the connection between the ring and the nucleus through spectroscopic analysis of the red shift. This shift is due to the expansion of the universe, with more distant objects exhibiting a greater redshift. By analyzing the redshift of the core and ring of Hoag's object, astronomers confirmed that they're not separate entities, but components of the same galaxy. This discovery debunked the gravitational lens hypothesis and cemented the status of the Hoag object as a unique type of galaxy. The central core, consisting of old red stars, contrasts sharply with the outer ring, which is bright blue and actively forming new stars. It is this special composition and structure that distinguishes Hoag's object from typical spiral and elliptical galaxies. Ring galaxies are rare, making up less than 0.1% of all known galaxies. Typical spiral galaxies have sprawling arms of stars, while elliptical galaxies have a more uniform, rounded shape. The Hoag object, with its perfectly separated nucleus and ring, remains one of the most well-defined examples of this rare class of galaxies. The discovery began the scientific journey to understand one of the most mysterious structures in the universe. Today, with the help of modern telescopes and ongoing research, astronomers are trying to unravel the mysteries surrounding this fascinating cosmic anomaly. Its quiet appearance, distinct breakup, and combination of an ancient core with a young, star-forming ring make Object Hoag a unique and enigmatic galaxy, prompting astronomers to investigate various theories of its origin and evolution. Thus, one of the main theories proposed to explain the formation of the Hoag object is the collision hypothesis. According to this theory, the characteristic ring structure of the galaxy arose as a result of a high-speed collision of a smaller galaxy with a larger one. When a smaller galaxy collides with a larger galaxy, the impact generates a density wave that rushes outward from the center of the larger galaxy. This wave compresses the interstellar gas, causing star formation in the ring around the galaxy's nucleus. The Cartwheel galaxy, with its strikingly similar ring structure, is a classic example of this process. In the case of a Hoag object, if a smaller galaxy collided with it, we would expect to detect several key features. First, the collision would create density waves that push the gas and stars outward, forming a ring. Moreover, the stars in the ring should have exhibited high relative velocities, indicating the kinetic energy from the collision. And third, in or near the ring, there would be residual fragments or remnants of colliding galaxies. However, detailed observations of Hoag's object have revealed some inconsistencies with the collision hypothesis. The ring stars do not exhibit the high relative velocities that are usually associated with such events. In addition, there's a notable absence of residual fragments or evidence of a second galaxy. To test this hypothesis, models of galaxy collisions have been used. These models show that, although a collision may produce a ring structure, the resulting galaxy often retains traces of violent interaction. The Hoag object, which has a calm and symmetrical appearance, lacks these chaotic features, suggesting a more complex formation history. However, another intriguing possibility looms on the horizon: resonance theory. Could a galaxy's ring structure be the result of gravitational interactions within a spiral galaxy? Let's explore this question. Another fascinating theory explaining the formation of the Hoag object is the resonance theory. According to this theory, the ring structure of a galaxy can arise as a result of the internal dynamics of barred spiral galaxies, in particular due to resonance in the gravitational field. Spiral galaxies are characterized by the structure of a central bar, from the ends of which spiral arms branch off. These bars play a crucial role in the dynamics and evolution of the galaxy. According to theory, as the bar rotates, it can create a resonance that affects the distribution of gas and stars within the galaxy. Resonance occurs when gravitational forces within a galaxy create regions in which the rotational velocities of stars and gas clouds synchronize. These regions can trap gas and stars, resulting in the formation of rings. There are several basic types of resonances. Inner Lindblad resonance occurs near a galaxy center, often forming an inner ring. Outer Lindblad resonance arising further, potentially forming an outer ring. The third type is co-rotation resonance, a region where the rotational velocity of the bar coincides with the orbital velocity of the stars and gas, which can also lead to ring formation. In the case of the Hoag object, the presence of a ring around the elliptical core suggests that such resonances may have played a role in its formation. The bar structure could have caused a resonance that trapped gas and stars at certain radii, creating the distinct ring we see today. When the bar rotates, it exerts a gravitational influence that can reorganize the gas and stars of the galaxy. Over time, this process can lead to the formation of a well-defined ring structure. Resonance theory provides a mechanism for how a spiral galaxy can evolve into a ring galaxy without a collision. NGC 1291 is a classic example of a galaxy in which resonance effects likely played a role in ring formation. The central band and outer ring provide a visual analogy of what may have happened in Hoag's object. However, the resonance theory faces difficulties when applied to the Hoag object. In particular, the Hoag object currently has no central bar. This absence raises the question of whether the bar may have existed in the past and subsequently dissipated, or whether other processes may have contributed to the formation of the ring. However, there is another interesting and equally plausible theory: the accretion theory. Can the gradual accumulation of intergalactic gas explain the unique structure of the galaxy? Let's explore this in more detail. The third major theory proposed to explain the formation of the Hoag object is the accretion theory. According to this theory, the unique structure of the galaxy resulted from the gradual accumulation of intergalactic gas, rather than from a dramatic collision or internal resonance. Accretion is the process by which a galaxy collects gas from the surrounding intergalactic medium over a long period of time. This gas is entrained by gravitational attraction, gradually accumulating and forming new structures. In the case of the Hoag object, it's likely that a central elliptical core formed first. Over time, the gravity of this core attracted gas from the intergalactic medium. As the gas approached the nucleus, it began to rotate around it, forming a ring structure due to angular momentum conservation. As gas accumulated in the ring, its density reached a high enough density to trigger star formation. This process explains the bright blue color of the ring, indicating active, ongoing star formation. And the gap between the core and the ring is explained by the balance of gravitational forces and the dynamics of the infalling gas. Galaxies such as NGC 6028 provide an example of how accretion can lead to the formation of ring structures. These galaxies show similar features: older central nuclei and younger rings of star-forming regions, which supports accretion theory as a plausible explanation. While the accretion theory provides a plausible explanation, it also raises questions. Why does the ring form at a particular radius? How did the dynamics of gas influx and star formation balance create such a clear separation between the core and the ring? These questions continue to drive research and exploration. Continued observations have provided evidence to support this theory. The ring of Hoag's object contains more gas mass than the entire Milky Way, suggesting significant accretion of intergalactic material. In addition, the well-defined structure of the ring and the absence of chaotic remnants are consistent with a gradual and orderly accretion process. Recent research has also significantly deepened this theory. By modeling the gravitational interaction in such ring systems, scientists have shown how the balance of forces can create stable and unstable orbits, leading to discontinuities in the distribution of matter. These results are consistent with the observed structure of the Hoag object, where the gap between the core and the ring is a region of unstable circular orbits, further supporting the theory. Also, the accretion theory offers a quite convincing explanation for the formation, suggesting that the galaxy grew and evolved through the slow accumulation of surrounding gas. This process contrasts with the more violent and destructive events described in the collision and resonance theories. However, each of these proposed theories, collision, resonance, and accretion, has their own flaws, leaving several unanswered questions. Although the collision hypothesis explains the formation of the ring by density waves created by galaxy collisions, it does not explain the ordered structure of the object and the absence of residual fragments and high relative velocities commonly observed in such events. Resonance theory, on the other hand, suggests that internal gravitational resonances within a twisted spiral galaxy can create ring structures. However, it's clear that Hoag's object lacks the central bar necessary for this process, and the theory does not fully explain the apparent gap between the nucleus and the ring. Accretion theory, in turn, argues that the gradual accumulation of intergalactic gas forms a ring. While this explains the ordered structure and ongoing star formation, questions arise as to why the ring forms at a particular radius, and how the dynamics between the core and the ring create such a distinct gap. Despite these theories, several mysteries remain. Why is there a significant gap between the nucleus and the ring? What specific conditions led to the formation of such a well-defined structure? And how do gravitational forces and dynamics within the galaxy interact to maintain this balance? Future telescope missions, such as the Nancy Grace Roman Space Telescope and the soon-to-be-launched Extremely Large Telescope, are designed to provide a deeper understanding of such questions. These advanced observatories will provide higher resolution images and more detailed spectroscopic data, potentially revealing the processes underlying the formation of such ring galaxies. As we explore the cosmos, Hoag's object remains a testament to the diverse and complex processes that form galaxies, and remind us once again that there are still mysteries in the cosmos waiting to be discovered. Reality. We think we know what it is. The ground beneath our feet, the air we breathe, the world we see. But the deeper we look, the stranger it becomes. Did you know that what we perceive as solid matter is mostly space? The atoms that make up everything around us are 99.9% space. In addition, there is time. It's not a constant, ticking away in the background. Time can stretch, slow down, and even stop under the right conditions. So how much of what we experience is real, and how much is just a construct of our minds? What if the reality we trust is just a shadow of something deeper, stranger, and infinitely more complex? What is reality? For the first humans, the answer was simple. Reality was what they could see, hear, touch, and smell. The world around them was interpreted through their senses, guiding them through every day. The rustling of leaves signaled the approach of a predator. The distant crack of a branch indicated prey, and the sensation of warmth from a campfire chased away the cold night. This sensory reality was everything. Survival depended on it. Sight, hearing, touch, smell, these senses were the tools with which they cognized their environment. But for them, reality was limited to that which was accessible to direct perception. The invisible world beyond their senses was incomprehensible. Everything tangible became real. If a sound was heard, the danger was near. If an odor was smelled, food could be found. If something could not be smelled, it might not exist at all. Survival was a continuous process of interpreting these sensory cues, often in life or death situations. Recognizing the difference between the roar of a predator and the rustle of the wind could mean the difference between safety and death. Early humans lived in a world where reality was directly related to their immediate needs: food, shelter, protection. For them, reality was not questioned, it was lived through experience. However, as society evolved, the concept of reality also changed. The question of existence and meaning began to extend beyond the immediate environment. What lies beyond the senses? What forces shape the world? Over time, the limitations of direct perception have given way to imagination and conjecture. This curiosity led to the birth of new ideas, a reality that was no longer tied to the physical world. Early humans began to develop explanations for what they could not see or understand. Spirits, gods, and forces of nature became personifications of the unknown. Fire, lightning, and stars were attributed to forces beyond human control. Through mythology and beliefs, they created a wider reality that filled the gaps left by their sensory limitations. This cultural development marked a turning point in human thinking. Humanity's journey, which began with a simple need to survive, has now evolved into something much more complex. In one of the earliest philosophical explorations of reality, Plato presents this allegory of the cave. In this mental experiment, prisoners have been confined in a cave all their lives, seeing nothing but shadows projected on the wall in front of them. These shadows are all they know about. They mistake these flickering figures for reality itself. For them, the shadows are the only truth that they can perceive. But what if they broke free of their chains and turned around? What would they see? Plato's allegory suggests that human perception is often limited. What we perceive as reality may only be a shadow of a deeper, truer existence. The path to understanding true reality, Plato argued, begins with questioning the world as we perceive it. Plato's allegory is not just a philosophical exercise. It is a profound commentary on the limits of human perception. We may think we see the whole picture, but we're often limited by the limits of our senses and our experience. Reality can thus extend far beyond what we can directly observe. In the physical world, our understanding of reality underwent a significant change with the discovery of space-time. In the early 20th century, Albert Einstein shattered the age-old foundation of classical physics by showing that space and time are not separate entities, as previously thought, but are instead interwoven into a single four-dimensional fabric, space-time. According to Einstein's general theory of relativity, massive objects warp this fabric, creating what we experience as gravity. Planets revolve around the sun, not because they're pulled by some invisible force, but because the sun warps space-time around itself, creating a curved path for them. This revolutionary concept has completely changed our view of reality on a cosmic scale. Time, too, is no longer absolute. In Einstein's universe, time can be stretched or compressed, depending on the speed at which an object is moving, or its proximity to a more massive object. This idea, time dilation, means that time itself is relative, which changes our perception of how reality unfolds. The scientific method has for centuries allowed us to peel back the layers of this reality. Classical mechanics, developed by Newton, gave us the tools to understand the motion of objects by accurately predicting their trajectories. But as we began to delve deeper into the nature of the universe, discoveries, especially in quantum mechanics and relativity theory, showed us that reality operates in ways that had previously defied common sense. The search for the basic building blocks of reality began thousands of years ago. Back in the 5th century BC, the Greek philosopher Democritus suggested that everything in the universe consists of tiny, indivisible particles, atoms. These atoms, he argued, are the fundamental building blocks of all matter. This idea persisted for centuries until modern atomic theory took shape in the 19th century. Scientists such as John Dalton began to provide empirical evidence that all matter was indeed made up of atoms. These tiny particles, invisible to the naked eye, joined together in various ways to form everything from the air we breathe to the stars in the sky. Atoms were long thought to be the most fundamental, indivisible units of the physical world. But as our understanding deepened, we discovered that the atom itself could be broken down into even smaller particles. In the early 20th century, the discovery of subatomic particles, protons, neutrons, and electrons, showed that atoms were not indivisible after all. These subatomic components opened the door to a whole new field of physics, quantum mechanics. Quantum mechanics offered a radically different view of reality. At the atomic level, particles behave in ways that defy the rules of classical physics. Electrons don't just revolve around the nucleus in neat, predictable trajectories. Instead, they exist as probabilities. Their location not fixed until they are observed. This strange behavior introduces the concept of superposition, Particles can exist in multiple states simultaneously until they're measured. At this level, the very nature of reality itself becomes uncertain. Classical physics taught us that the universe works like a precise machine with predictable cause and effect relationships. But quantum mechanics has shown that reality, at its core, is governed by probabilities. This new understanding challenged the notion of a solid, deterministic universe and replaced it with one in which randomness and uncertainty reign. So, as our understanding of the atom deepened, it became clear that even protons and neutrons, the components of the atomic nucleus, are not the most fundamental units of matter. Within these particles, scientists have discovered quarks, elementary particles that come together in certain combinations to form protons and neutrons. Alongside them were particles called gluons, which are responsible for binding quarks together, acting as mediators of the strong force, the fundamental interaction that holds the atomic nucleus together. Quarks, however, are unlike anything else in the world of physics. They cannot exist individually, only in combinations, bound together by a strong force. This force is so powerful that trying to separate quarks results in more quarks. It is a strange and complex system that continues to challenge our understanding of the fundamental structure of matter. Subatomic physics, and especially the study of quarks and gluons, has pushed the boundaries of our knowledge, making it even more uncharted. Although the standard model of particle physics successfully explains many particles and forces in the universe, deeper questions remain. How do these particles interact at the most fundamental level? What are the true building blocks of reality? One of the boldest theories in the search for answers to these questions is string theory. This revolutionary idea suggests that the fundamental particles we observe, quarks, electrons, and others, are not point particles at all, but tiny one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the different types of particles we observe. String theory is not limited to the redefinition of particles. It suggests that these strings exist not only in the familiar three dimensions of space and one dimension of time, but also in multiple dimensions, perhaps 10 or 11. These additional dimensions are beyond our immediate perception. They're coiled so tightly that they remain hidden from view. If string theory is correct, then reality may be far more intricate than we ever imagined and extend into realms we've yet to observe. And this brings us to Copenhagen interpretation, one of the most famous philosophical foundations for understanding quantum mechanics. Proposed by physicist Niels Bohr, this interpretation is based on the idea that quantum particles do not possess certain properties until they are measured. Before observation, they exist only as probabilities. It's the act of measurement, the interaction with a conscious observer, that gives rise to reality. In other words, until you observe a particle, its state is fundamentally undefined, neither here nor there. However, not all physicists are satisfied with the Copenhagen interpretation. Some prefer the more radical, many worlds theory, first proposed by Hugh Everett. According to this interpretation, every time a quantum event occurs, every time a particle's wave function collapses, the universe splits. In one universe, the particle follows one path. In another, it follows a different path. Instead of converging to one outcome, all possible outcomes occur, but in different branching universes. These parallel worlds exist simultaneously, each representing a different version of reality. The theory of multiple worlds provides an alternative to the idea that observation leads to a so-called collapse of reality. Instead, it argues that all possible realities exist, but we're only aware of the one we live in. This is a striking concept. It expands the imagination and makes us think that reality is much more layered than we see in everyday life. Whether we adhere to the Copenhagen interpretation, the many worlds theory, or some other explanation, one thing is clear. At the quantum level, the rules of reality are not at all what they seem. Despite its elegance, however, string theory remains largely unproven. The theory operates on such small scales that modern technology can't yet test its predictions. Even with all of our advances in subatomic physics, there is still much we do not know. Quantum mechanics and general relativity, the two pillars of modern physics, are still incompatible with each other, especially when it comes to explaining gravity on the smallest scales. While the Standard Model describes known particles and forces, it fails to account for dark matter, dark energy, and a complete explanation of gravity, suggesting that there's much more to reality than we can perceive or measure. So the question arises, where are you now? Not in the physical sense or location, but in the sense of experience. Your consciousness is the lens through which reality is perceived. But what exactly is consciousness? Is it simply the result of electrical signals and chemical reactions in the brain? Or is it something more? A fundamental part of reality itself? For much of modern science, consciousness has been understood as a byproduct of the brain, an emergent property arising from the complexity of neurological processes. Billions of neurons working in concert to form complex networks generate everything we feel, think, and perceive. From this perspective, consciousness is simply what happens when the brain reaches a certain level of complexity. But this explanation does not fully solve the mystery. The hard problem of consciousness is how philosopher David Chambers put it, is the question of how and why subjective experience, a sense of awareness, arises from purely physical processes. Why should a particular arrangement of neurons produce a vivid inner world of visual images, sounds, emotions, and thoughts? The gap between the physical workings of the brain and the richness of conscious experience remains one of the most confusing questions in science and philosophy. Some argue that consciousness is not just a byproduct of matter, but something much more fundamental. Some theories suggest that consciousness may be woven into the very fabric of reality, much like space and time. This idea, known as panpsychism, asserts that consciousness is not limited to humans or animals, but is a basic property of all matter, pervading the universe to some degree. So, if consciousness is fundamental, it could mean that the universe itself has consciousness to some extent. This shifts the question from how does the brain produce consciousness to how does consciousness manifest itself through matter? This in turn suggests that the distinction between mind and matter may be artificial, that consciousness and the material world are deeply interconnected. Other theories offer a more traditional approach. Consciousness is an emergent property. According to this view, the complexity of the brain creates consciousness in the same way that water emerges from individual hydrogen and oxygen molecules. In this view, consciousness is completely dependent on the physical structure of the brain. When the brain ceases to function, consciousness disappears. But this explanation still leaves unanswered the fundamental riddle of subjective experience. Philosophers and scientists have debated the true nature of consciousness for centuries. Is it reducible to material processes? Or is it something more, something that perhaps eludes our current understanding of physics and biology? If consciousness plays a role in shaping what we perceive as reality, could it be that our subjective experience is not just a reflection of reality, but part of its very foundation? Ultimately, the nature of consciousness remains one of the greatest mysteries. What is it about consciousness that distinguishes it from everything else in the universe? Is consciousness a window into a deeper level of reality, or just a byproduct of complex physical systems? The question of where you are, where consciousness fits into the grand plot of existence, remains an open question. The more we learn about the brain and the universe, the clearer it becomes that reality may be far more intricate than we can currently comprehend. Perhaps one day, discoveries will show that consciousness is not just something happening inside reality, but a fundamental key to understanding reality itself. Imagine a civilization so advanced that it can build colossal structures around stars, capturing their energy and using it for unimaginable purposes. This is not the realm of science fiction. It's a concept proposed by one of the most brilliant minds of the 20th century. A visionary physicist, Freeman Dyson, envisioned a megastructure capable of enveloping a star, capturing its vast amounts of energy. This idea, while radical, is rooted in the basic principles of energy consumption and technological progress. But why would an advanced civilization need such a structure? As our civilization advances, our energy needs grow exponentially. But our most ambitious projects pale in comparison to the energy output of our Sun, which releases more energy in 1 second than humanity has consumed in its entire history. Imagine harvesting every bit of a star's energy, turning it into a power plant with nearly limitless potential. If realized, this colossal undertaking would revolutionize how we think about energy and its possibilities. But what would such a structure look like? And even more intriguingly, how would we be able to detect it from our distant vantage point here on Earth? The problem lies in our ability to detect signs of such advanced engineering. While we are just beginning to tap into our planet's energy resources, discovering such an advanced civilization is exciting and frightening. Recent research has revealed unusual infrared signals from 7 distant stars, sparking debate and fueling imagination. Could these signals be technosignatures? Either way, these anomalies defy natural explanations. What's behind these mysterious infrared glows? Are they evidence of advanced extraterrestrial engineering or natural phenomena that we've yet to understand? To understand the concept of Dyson spheres, we must first familiarize ourselves with the Kardashev scale, a method of measuring a civilization's level of technological development based on its energy consumption. In 1964, Soviet astrophysicist Nikolai Kardashev proposed this scale, dividing civilizations into 3 types, depending on their energy consumption. Type 1 civilizations use all the energy available on their home planet, including geothermal, solar, wind, and other natural energy sources. Imagine controlling the power of earthquakes and volcanoes to power our cities. This is the hallmark of a Type 1 civilization. Civilizations of the second type go even further, receiving energy directly from their star. This is where the Dyson spheres comes into play. By surrounding their star with massive structures, these civilizations can use almost all of its energy. Type 3 civilizations, in turn, are even more advanced and can harvest and harness the energy of their entire galaxy. They control the energy of billions of stars, making them unimaginably powerful. The relevance of the Kardashev scale to Dyson spheres lies in the connection between energy consumption and technological progress. As civilizations evolve, their energy needs grow exponentially, forcing them to develop ever more ambitious methods of meeting those needs. But how can we discover the Dyson sphere? One of the most significant milestones in cosmic observation, the development of infrared astronomy, can help us in this challenging endeavor. Infrared astronomy allows us to see the universe in a new light, literally. By observing the infrared spectrum, scientists can detect heat emitted by celestial objects and reveal details invisible to traditional telescopes. This capability has played a crucial role in the search for technosignatures, signs of advanced civilizations beyond Earth. This journey began in the mid-20th century, when astronomers used infrared sensors to study space. These early works laid the groundwork for today's sophisticated infrared observatories. such as the Wide Field Infrared Survey Explorer, WISE, and the James Webb Space Telescope. These instruments have opened a new frontier in astronomy, allowing us to detect faint thermal signals from distant stars and galaxies. But what does this have to do with the search for Dyson spheres? Well, in the 60s, theoretical physicist Freeman Dyson proposed an audacious idea. An advanced civilization could build a massive structure around its star to capture its energy. He envisioned a swarm of solar collectors or habitats orbiting the star and forming what we now call a Dyson sphere. But how could it possibly be detected if it blocked the light of its star? Of course, such a structure would emit vast amounts of infrared radiation, making it visible even from Earth. Dyson's hypothesis was more than just a thought experiment. It provided a viable way to search for intelligent extraterrestrial life. By surveying the excess infrared radiation around stars, we could find evidence for the existence of these colossal structures. This concept led scientists to the recent discovery of several stars with unusual infrared emission. Modern infrared astronomy opens new horizons in the search for Dyson spheres and other technosignatures. By observing the universe in the infrared wavelength range, we can detect thermal emission from celestial objects, allowing us to understand phenomena invisible to traditional optical telescopes. One of the most important instruments in this work is the Wide Field Infrared Survey Explorer. Launched in 2009, WISE has revolutionized our understanding of the infrared universe. Its mission is to map the entire sky in infrared light, revealing countless celestial objects, including stars, galaxies, and asteroids. This is a mosaic of the images covering the entire sky, as observed by the WISE, part of its all-sky data release. WISE's ability to detect excess infrared emission around stars plays an essential role in the search for Dyson spheres. By analyzing the heat signatures recorded by WISE, scientists can identify stars with unusual infrared emission, which may indicate the presence of advanced megastructures. One prominent example is the Hephaestus project, led by a team from Uppsala University. This ambitious initiative aims to identify potential candidate Dyson spheres by analyzing Gaia, 2MASS, and WISE data. Hephaestus uses a sophisticated system to sift through millions of stars in search of those with excess infrared emission that natural phenomena cannot easily explain. The project uses machine learning algorithms, including convolutional neural networks, to weed out false positives and identify the most promising candidates. The project's methodology is rigorous. It begins by collecting data from several sources, including precise measurements of the position and distance of the stars using Gaia, near-infrared 2MASS observations, and mid-infrared WISE data. This comprehensive dataset allows the team to create detailed models of potential Dyson spheres. The team then uses a grid search method to compare the observed data with theoretical models. This involves calculating the expected infrared emission for different configurations and temperatures of Dyson spheres, and then comparing these models to the observed infrared excess. Through this careful process, Hephaestus has identified 7 potential candidates for a Dyson sphere. All of these objects are M-dwarfs, stars known for their relatively low luminosity, making the detection of infrared excess even more intriguing. These findings are significant because they demonstrate the potential for using long-standing astronomical data for such detections. The quest to detect Dyson spheres and other technosigns is driven by ongoing advances in infrared astronomy. These innovations allow us to explore the universe with unprecedented precision and detail. One of the most significant breakthroughs in infrared astronomy is the development of adaptive optics and advanced sensors. Adaptive optic systems correct for distortions caused by the Earth's atmosphere, providing clearer and more detailed images of celestial objects. This technology is vital for isolating faint infrared signals from background noise. In addition, integrating machine learning algorithms into data analysis has revolutionized our ability to sift through vast amounts of astronomical data. These algorithms can identify subtle patterns and anomalies that may indicate the presence of technosignatures. Among the most revolutionary achievements is the James Webb Space Telescope, which has already managed to change our understanding of the cosmos in more ways than one. With its advanced infrared capabilities, the JWST allows us to look deeper into space and time than ever before. JWST's primary mirror, which is more than 16 times larger than the WISE mirror, combined with susceptible infrared instruments, can detect the faintest thermal signals from distant stars and galaxies. Essential is the telescope's ability to observe in the mid-infrared region of the spectrum. If they exist, Dyson spheres are likely to emit heat in this range, making them visible to JWST. By scanning the sky for these infrared signatures, JWST could provide compelling evidence for the existence of advanced extraterrestrial civilizations. However, its busy schedule, planned months in advance and filled with many other important research projects, limits the amount of time for searching for Dyson spheres. Radio astronomy, in addition to infrared observations, plays no small role in the search for technosigns. The Very Large Array in New Mexico is one of the world's premier radio observatories, capable of detecting radio waves across the universe. Radio waves can provide important information about the presence and nature of technosignatures. For example, a Dyson sphere may emit infrared radiation and radio signals as a byproduct of energy harvesting processes. VLA can detect these signals, offering a different but complementary perspective to infrared observations. Developing and implementing advanced technologies will only improve our ability to find technosignatures. However, the results of the team from the Uppsala University are not isolated. Another recent study entitled A Data-Driven Search for Mid-Infrared Excesses Among 5 Million Main Sequence FGK Stars by Gabriela Contardo and David W. Hoag found 53 stars with significant infrared excesses. This large-scale search also used Gaia, DR3, 2MASS, and WISE data to detect anomalies in the mid-infrared range. The technique involved training machine learning models to predict expected infrared magnitudes based on other stellar characteristics. Stars in some bands appeared significantly brighter than predicted, and thus were flagged as potential candidates. After applying additional filters to help avoid false positives, the study narrowed the 4.9 million sample to 53 stars. Analysis of these findings reveals several intriguing candidates. For example, one of the identified stars shows an infrared excess consistent with extreme debris disk characteristics, which could be mistaken for a technosignature. However, its older age calls into question existing models of planet formation, suggesting either an extended disk evolution or alternative processes. The implications of these discoveries are profound. If any of these infrared anomalies are indeed Dyson spheres, it would provide direct evidence of the existence of advanced extraterrestrial civilizations. However, the scientific community remains cautious. Natural phenomena such as dust clouds or the extreme debris disk can also provide similar infrared signatures. Therefore, each candidate requires careful follow-up observations to confirm or deny the presence of artificial structures. The controversy surrounding these findings emphasizes the difficulty distinguishing between natural and artificial sources of excess infrared radiation. Indeed, in general, the vast distances between Earth and potential candidates pose a severe problem. Many of the stars under study are thousands of light years away, making detecting and analyzing their infrared signatures extremely difficult. The farther away a star is, the fainter its signals are, and the harder it is to obtain good quality, accurate data. Some scientists argue that our current understanding of stellar and planetary dynamics is incomplete, and these anomalies may reveal new astrophysical phenomena rather than technosignatures. The search for extraterrestrial life has gripped humanity for centuries, evolving from philosophical speculation to a rigorous scientific approach. Today, scientists use various methods to detect signs of life beyond Earth, focusing on technosignatures and biosignatures. While technosignatures are indicators of advanced technological activity, including large-scale structures like Dyson spheres, unusual energy emissions, or artificial signals, biosignatures, on the other hand, are indicators of biological activity. They can range from detecting specific gases in a planet's atmosphere, such as oxygen and methane, to surface features indicative of life. Current and upcoming missions are crucial in detecting these subtle signs of life. For example, the James Webb Space Telescope can observe in the infrared, detecting the faint heat signatures of distant exoplanets and their atmospheres. This provides valuable data on potential conditions suitable for life. It has confirmed dozens of potentially habitable exoplanets in the past year alone. Another important initiative that goes shoulder to shoulder with JWST is TESS, the Transiting Exoplanet Survey Satellite, which aims to detect exoplanets by observing their transits through stars. TESS has already identified thousands of exoplanet candidates, many prime targets for further study with more powerful telescopes, such as Webb. Future missions promise to further enhance our ability to detect technosigns and biosigns. The proposed LUVOIR, Large UV Optical IR Surveyor, and HABEX, Habitable Exoplanet Observatory missions, are designed to directly image exoplanets and analyze their atmospheres. These next-generation telescopes will provide unprecedented clarity and sensitivity, allowing us to detect even the faintest sign of life or advanced technology. In addition to space observatories, ground-based telescopes, such as the Extremely Large Telescope and Square Kilometer Array, will play a crucial role. ELT, with its massive mirror, will be able to obtain direct images of exoplanets and study their atmospheres in detail. At the same time, SKA will focus on detecting radio signals from space that could indicate technological activity. The search for life is not limited to looking for existing civilizations. Scientists are also exploring the possibility of life in our solar system, focusing on moons such as Europa and Enceladus, which have subsurface oceans. Missions such as Europa Clipper and potential future missions to Enceladus aim to detect signs of microbial life in these hidden waters. As we continually refine our methods and technologies, each discovery, whether it confirms or disproves the existence of life, brings us closer to understanding our place in the universe. The journey is as important as the destination. It pushes the boundaries of science and ignites our collective imagination. And each innovation brings us closer to answering one of humanity's deepest questions. Are we alone in the universe? In the infinite depths of the universe lies a fundamental principle, as mysterious as it is omnipresent. This force governs the very fabric of existence, yet remains elusive to the casual observer. This is the story of entropy, a concept that reveals the hidden order in the apparent chaos of the cosmos. Here on Earth, entropy is evident in every rustling leaf, every rolling wave, and every moving cloud. It's the quiet organizer of natural processes, from the simplest to the most complex. But what is entropy really? It's a phenomenon often misunderstood as an ordinary disorder, but it's more than that. Entropy is a transformation, a movement from order to disorder, from concentration to dissipation. This is exactly why your coffee gets cold, why the ice melts, why the scent of flowers dissipates in the air. So let us understand how an order is hidden in what appears to be chaos, and how does this mysterious force shape our entire environment, from the smallest particle to the largest galaxy, and even the very course of life itself. There is a hidden force at work in every corner of our world, from the quiet forests to the bustling hearts of our cities. This force, often unnoticed, plays a key role in the great work of the universe. Imagine a dewdrop on a leaf, shimmering in the morning sunlight. As the sun rises, the dewdrop slowly disappears, and its particles disperse into the air. This phenomenon illustrates a fundamental principle of nature: the transition from a concentrated state, the dewdrop, to a dispersed state, the water vapor in the air. At the molecular level, this principle manifests itself as the tendency of particles to move from a state of concentration to a state of dispersion. This is similar to the way a crowd disperses after a concert, moving from a structured gathering to random scattered groups. In the center of our cities, this principle is reflected in the rhythm of daily life. The concentrated bustle of the morning rush hour gradually fades away as the day progresses. Entropy is often misunderstood as simple chaos or disorder, but it's much more nuanced than that. It's about transformation and change. Like a sandcastle slowly crumbling under the merciless waves, entropy is the inevitable transition from order to disorder. This concept is encapsulated in the second law of thermodynamics, a fundamental principle of physics. It states that in any closed system, entropy will either remain constant or increase over time. In other words, the natural course of the universe is toward greater dispersion and disorder. From the grand scale of the cosmos, where stars and galaxies form and disappear, to the minutiae of our daily lives. This principle is a universal constant. It governs the birth and death of stars, the flow of rivers, and even the fading heat in a coffee cup. Imagine a steaming cup of coffee left on a table. Over time, its heat dissipates into the surrounding air, cooling the coffee. This is entropy in action, redistributing energy from a concentrated state, hot coffee, to a more diffuse state, a cold room. Or take an ice cube melting on a warm day. The structured, solid form of ice turns into a puddle of water, whose molecules are free to move. This transition from a solid, ordered state to a fluid, disordered state is a classic example of increasing entropy. In every aspect of our universe, this quiet but relentless force is always present, subtly directing the flow of energy and matter. As we delve deeper into the theory, it's crucial to go back in time to the era when the concept first emerged. The history of entropy is intertwined with the minds of some of the most brilliant scientists in history. Our narrative begins with Sadi Carnot, a French physicist often referred to as the father of thermodynamics. In the early 19th century, Carnot was fascinated by the efficiency of steam engines, the driving force behind the Industrial Revolution. His research laid the foundation for the laws of thermodynamics, which were later incorporated into the concept of entropy. Carnot's visionary work described how heat engines work and focused on how energy is transferred and transformed. His theories have played a crucial role in understanding the dynamics of energy flow within systems. The next key figure in our story is Rudolf Clausius, a German physicist. Clausius was the one who introduced the term entropy in the mid-19th century. He built on Carnot's ideas by delving into the nature of heat and energy transfer. Clausius's work led to a more formal definition of entropy. He suggested that heat cannot spontaneously transfer from a colder body to a hotter one, the principle underlying the second law of thermodynamics. His mathematical formulation of this concept allowed it to be quantified, bringing clarity to its elusive nature. Another giant in this field was Ludwig Boltzmann, an Austrian physicist. Boltzmann's contributions in the late 19th century brought a statistical approach to thermodynamics. He linked the microscopic behavior of atoms and molecules to macroscopic properties of matter, such as temperature and entropy. Boltzmann's work was groundbreaking. He showed that entropy can be understood as a measure of disorder at the molecular level. His famous formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microstates, gave a profound insight into the nature of this phenomenon. The legacy of these pioneering scientists is immense. Their collective work laid the foundation for modern thermodynamics and statistical mechanics, fields that continue to evolve and shape our understanding of the universe. Turning our gaze to the natural world, we find that entropy is at work in every ecosystem, shaping the environment and the life within it. Nature, in its infinite complexity, is a vivid canvas of disorder in action. Consider a fallen tree in the forest. Over time, it undergoes a remarkable transformation. Microorganisms, insects, and fungi break it down, returning nutrients to the soil. This process of decay and renewal is a manifestation of our principle, reflecting the cycle of life and death in nature. Rivers are also agents of entropy. They constantly change the landscape, cutting through rock and soil, and redistributing sediments from the mountains to the sea. This relentless movement and transformation of matter is a classic example of the role of this principle in geophysical processes. Weather is another area in which chaos plays a crucial role. Cloud formation, rainfall, snowmelt. These are all processes driven by the distribution and redistribution of energy in the atmosphere on a global scale. In the oceans, entropy is manifested in the life cycles of marine ecosystems. Coral reefs, for example, thrive on the delicate balance of nutrient cycles, temperature, and ocean currents governed by the principles of energy flow. Photosynthesis, the process by which plants convert sunlight into energy, is another interesting example. Here, the entropy principle plays a role in converting solar energy into chemical energy, a process fundamental to life on Earth. From the tiniest interactions of microscopic organisms to the grandeur of ecological systems, this fundamental force is the invisible conductor of the natural world. It is the underlying principle that nurtures the beauty and dynamism of our planet. Life on Earth, in all its diverse forms, is deeply intertwined with the principles of energy flow and transformation. This complex relationship between life and energy reveals a universe in which chaos and order coexist in a delicate balance. Consider the simple process of seed germination. This process is a microcosm of life's ability to use and organize energy. As the seed grows, it absorbs energy from the environment, converting it into structured, organized forms. However, there's a price to pay for this organization, an increase in the overall disorderliness of the system. In the human body, entropy is our constant companion. Our cells are energy conversion power plants, constantly converting nutrients into energy. This metabolic activity is vital to our existence, but it also leads to increased disorder as energy is released in the form of heat and waste products. Ecosystems are also valid examples. For example, in a rainforest, the flow of energy from the sun to plants and then through the food chain demonstrates the role of entropy in ecological processes. Each transfer of energy from one organism to another involves energy dissipation, contributing to the overall disorder of the ecosystem. Looking at the bigger picture, the evolution of life on Earth can be seen as a journey through entropy, from the first single-celled organisms to the complex network of life we see today. Evolution has been a process of increasing complexity, driven by the fundamental laws of energy and matter. In the grand narrative of life, entropy is not just a concept of decay or disorder. It's the driving force behind growth, complexity, and a constant cycle of transformation. Life in all its forms thrives in the delicate balance between order and chaos, a testament to the profound interplay of energy and matter. In the cosmic arena, the principles governing entropy show a universe in constant motion, a stage in which stars are born, live, and die in a great cycle of energy transformation. Star formation is a process of remarkable energy dynamics. Inside nebula, clouds of gas and dust collapse under gravity, heating up and eventually triggering nuclear fusion. It's a transition from potential energy to kinetic energy, a cosmic example of energy distribution on an enormous scale. The life cycle of stars can be seen as a narrative of energy transformation. In their final moments, massive stars explode as supernovae, dispersing their elements across the cosmos. This dispersion is a powerful demonstration of the universe's tendency to increase the dispersion of energy and matter. Black holes, in turn, represent one of the most intriguing aspects of cosmic entropy. These mysterious objects, which have such a strong gravitational pull that even light cannot escape them, play a significant role in the energy dynamics of the universe. The black hole event horizon marks the point of no return, where matter and energy are irreversibly absorbed, contributing to the overall disorder of the cosmos. By the way, our channel has already published a detailed video about the connection between black holes, Hawking radiation that depletes them, and entropy. We recommend you watch it. The expansion of the universe is itself a confirmation of these principles. Galaxies are diverging, energy is becoming more evenly distributed over vast space, and the fabric of the cosmos is stretching, all of which indicate that the universe is evolving toward a state of higher dispersion. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a glimpse into the early universe. As we know, this radiation is a remnant of a time when the universe was hot, dense, and in a lower entropy state. Paradoxically, as the universe expanded and cooled, its randomness increased. And this is what led to the inevitable formation of the complex structures we see today. One of the most profound consequences of these cosmic processes is the concept of the heat death of the universe. In this scenario, the universe reaches a state of maximum entropy, where all energy is distributed so uniformly that further energy transformations become impossible. This is a future in which the universe is cold, dark, and devoid of the energetic dynamics that drive cosmic evolution. In this vast cosmic action, the flow and transformation of energy shapes not only the stars and galaxies, but also the very destiny of the universe. It is a continuous process of creation, transformation, and ultimately, disintegration. In the modern world, the concept of entropy has transcended its scientific origins, finding applications in a variety of fields, but subject to common misconceptions. Currently, entropy plays a crucial role in the development of advanced technologies. In the field of renewable energy, a thorough understanding of this concept is essential to improve the efficiency of solar panels, wind turbines, and energy storage systems. This knowledge greatly helps in optimizing the conversion of natural energy sources into usable energy. In the field of information theory, entropy has acquired a new meaning. It represents a measure of uncertainty or randomness in a system. This concept is crucial in data encryption and compression, where controlling and predicting information patterns is essential. Despite its scientific importance, entropy is often misinterpreted. A common misconception is to equate entropy solely with disorder or chaos. Meanwhile, while the definition that entropy leads to an increase in disorder is correct, it is worth clarifying that we're talking about the distribution of energy and the probability of certain states. Another misconception is the notion that entropy can be reversed or overcome. In popular culture, we see images of time reversal or spontaneous assembly of objects. However, according to the second law of thermodynamics, in a closed system, entropy can only increase or remain constant. Modern physics research is considering its impact on quantum mechanics, the behavior of black holes, and the ultimate fate of the universe. Beyond theoretical physics, entropy has practical applications in environmental science, engineering, and urban planning. It helps to model climate change, design sustainable systems, and understand urban development patterns. The future will undoubtedly bring new challenges and opportunities, and our understanding of this phenomenon will be critical in addressing them. Whether it is advancing technology, exploring space, or managing our planet and conserving its resources, entropy remains a fundamental concept that will continue to define our journey into the unknown. There is a hidden order in the void of space, a subtle force that controls the movements of the celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there is a mysterious harmony, a set of invisible rules that dictate the paths of planets, moons, and asteroids with remarkable precision. Consider for a moment that the giants of our solar system are not just isolated spheres of rock and gas, but participants in a grand gravitational party whose every move is influenced by the forces generated by their cosmic neighbors. Among the actors are Jupiter and its moons. Behind them also lies the asteroid belt, a vast ring of debris that holds voids of mysterious origin. These voids, devoid of the rocky features typically found in the rest of the belt, hint at an unseen participant silently shaping the structure of this cosmic phenomenon. Even distant Neptune and Pluto tell a tale of complex gravitational interaction, locked in such a precise rhythm that their paths never cross. These patterns and rhythms are constantly emerging in the vastness of space, hinting at the underlying order that governs the universe. Orbital resonance is the very concept behind this behavior. What forces act on this mechanism of behavior, both simple and bewilderingly complex at the same time? Let's find out. Behind the facade of the night sky, a complex network of forces operates to dictate the movements of celestial bodies. Gravity, the fundamental force that keeps our feet on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal furnace of nuclear energy whose gravitational pull subordinates the motions of the planets around it. This gravitational interaction is not a one-way street. Each planet, in turn, exerts its own gravitational pull, creating a complex network of forces that affect their orbits. When two celestial bodies come close together, their gravitational fields interact, influencing each other as if playing a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, an effect that's most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Consider the case of Jupiter, a giant of the solar system whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic, despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons that repeats over time, ensuring their long-term stability. The forces at work do not simply pull the moons along their trajectories, but push them to positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can lead to gaps in the asteroid belt, regions devoid of asteroids formed by the resonant effects of Jupiter's gravity. Based on the above, we can conclude that gravity acts as a weaver in the cosmos. Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order out of potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as easy to understand as it is obvious? In the gravitational embrace of Jupiter, the largest planet in our solar system, there is an amazing example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three previously mentioned major moons of Jupiter, Io, Europa, and Ganymede. Each of these moons, a wondrous world, is involved in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals, in a pattern that repeats itself every 7 Earth days. Resonance is not just a curious phenomenon. It has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, which promotes volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that persist over centuries. But the story doesn't end with satellites alone. Saturn, the jewel of our solar system, is surrounded by a series of mysterious rings. These rings are made up of countless particles of ice and rock, from a speck of dust to a mountain-sized lump. And yet, among this continuously glowing belt are gaps, vast stretches of emptiness that baffle. What had to happen for them to occur? One of these discontinuities, the Cassini separation, is evidence of the forces of orbital resonance. It's not simply a lack of material, but a boundary created by the gravitational influence of Saturn's moon, Mimas. Mimas's role in creating this gap is a fascinating example of orbital resonance in action. Mimas, although small compared to the gas giant around which it orbits, exerts a significant periodic gravitational influence on the particles inside the rings. This effect is not random. It occurs at specific points in the orbits of the particles, because their orbital periods are in resonance with the orbit of Mimas. For every 2 orbits that Mimas makes, the particles at the edge of the ring make 1, thus having a resonance in the ratio 2:1. Which leads to repeated gravitational interactions at the same point of the particle's orbits. These repeated interactions have a cumulative effect and act like a cosmic broom, clearing the way and creating the Cassini separation. Particles that once occupied this space were either pushed into new orbits or stuck together to form larger bodies, leaving behind the void that marks the boundary between Saturn's A and B rings. This process is akin to nudging a seesaw at just the right moments. Each nudge adds a little more energy to the system, and in the case of the planet's rings, each gravitational push by Mimas moves the particles around, clearing a path in the rings. However, the influence of Mimas and orbital resonance is not limited to the Cassini separation. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating a pattern of discontinuities and dense bands that make the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a huge cluster of rocky remnants from the era of the formation of the solar system. However, this region is unevenly filled. There are distinct gaps known as Kirkwood gaps. These gaps are not the result of missing asteroids, but represent areas where Jupiter's gravitational influence has organized stellar clearing. Kirkwood gaps are named after Daniel Kirkwood, who observed in the 19th century that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of the asteroid in the gap will have a simple ratio to Jupiter's orbital period, such as 1 to 2, 2 to 3, or 3 to 4. At such distances from the Sun, the asteroid's orbit will periodically align with Jupiter in a pattern that will be repeated at each orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, changing its orbit. When an asteroid falls into one of these resonance gaps, repeated gravitational jolts from Jupiter can increase the eccentricity of the asteroid's orbit, putting it on a more elliptical trajectory. This could cause the asteroid to move to a different orbit, leaving the resonance gap-free. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it approaches, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated pulls, pulling up slightly each time it completes its orbit. Eventually, these jolts can shift the asteroid's orbit, pushing it out of the resonance gap into a less perturbed region, where Jupiter's influence is less synchronized with its orbit. In the outer part of our solar system, beyond the gas giants and the icy Kuiper belt, lies another fascinating story of celestial harmony. Neptune, the 8th planet from the Sun, and Pluto, a dwarf planet in our system that was once considered the 9th, have a unique gravitational relationship that defies the odds of collision. This relationship is determined by the 3-to-2 resonance gravitational lock, which ensures that for every 3 revolutions of Neptune around the Sun, there are 2 revolutions of Pluto. This rhythmic interaction is not just a coincidence. The influence of this resonance is profound, shaping their orbital trajectory so that, despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, influenced by this resonance, is markedly eccentric and tilted as it winds above and below the plane of the solar system, balancing over millennia. This harmonious arrangement emphasizes the complex laws of physics that ensure stability and order in the vastness of space. But what do all these things have in common? The satellites, the planets themselves, their rings and asteroid belts. And why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on 3 key factors: eccentricity, a measure of the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether concerning a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined, determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body falls into resonance, its orbit becomes locked in a gravitational interaction with another body, usually a much larger one. This fixation can increase stability, as seen with Neptune and Pluto. However, there are simultaneous exceptions in which objects will be ejected from their trajectories, cutting gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process cannot be underestimated. A small increase in eccentricity, for example, can dramatically change the gravitational interaction of a body. bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we discover how the action of orbital resonance plays out on a grand cosmic stage, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where the planets keep pace with each other, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of the solar system themselves do not show a clear pattern of orbital resonance with each other. Their orbital periods don't have a simple integer ratio that would indicate resonance. While there are close resonances, such as the 5:2 resonance between Jupiter and Saturn, they're not as precise or stable as resonances between some moons, or in more dynamically bound systems such as Pluto and Neptune. The implications of these observations go far beyond simply cataloging celestial phenomena. They provide insight into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study such phenomena, each new study peels away another layer, revealing the intricate plan of the universe, bringing us closer to unraveling the fundamental principles that govern celestial motion and illuminating the very essence of our existence. What if the relentless forward march of time, the ticking of seconds, the changing of seasons, the aging of our bodies, is nothing more than a grand illusion? What if the past, present, and future, the cornerstones of our existence, don't truly exist in the way we believe? For centuries, these questions have haunted philosophers, scientists, and everyday minds alike. Is time woven into the very fabric of reality, or is it a stubbornly persistent trick our brains play on us? The deeper we delve into the mysteries of the cosmos, the more a tantalizing possibility emerges. What if our entire reality is a simulation? If so, could time simply be a programmed construct, a line of code within a vast, artificial universe? This concept forces us to question everything, even our most fundamental assumptions about the passage of moments. We often take time for granted, but it shares a surprising similarity with another constant in our lives: color. The colors we perceive are not inherent properties of objects themselves. Instead, they're creations of our brains as they interpret wavelengths of light. Could a similar process be happening with time? Perhaps our sense of temporal flow is a construct, a way for our minds to impose order and meaning on an otherwise timeless universe. Consider the vibrant world of color that surrounds us. A juicy red apple, a field of yellow sunflowers, clear blue of a summer sky. At first glance, these colors might seem like fixed properties of the objects themselves, yet the reality is far more complex. Colors don't exist independently in the world. They're born within our minds. Our eyes detect different wavelengths of light, and our brains translate those signals into the rich tapestry of hues that shape our visual experience. This process isn't merely about biology. People with different forms of color blindness perceive the world in distinct ways. Animals with different eye structures experience an even wider range of colors, some even seeing wavelengths invisible to us. What we call color is highly subjective, shaped by the unique capabilities of our sensory systems. Just as our perception of color is a creation of our minds, could the same be true of time? Perhaps the feeling of time ceaselessly flowing forward, the division of our lives into past, present, and future, is merely a way to make sense of change within the universe. Maybe, like color, time emerges from the interaction between our consciousness and a reality that may be fundamentally timeless. The idea that time may be an illusion isn't new. From ancient philosophers grappling with the nature of change to modern physicists unraveling the fabric of space-time, the question of time has persistently challenged our understanding. Today we're going to delve into this enigma, exploring the scientific discoveries and philosophical riddles that hint at the possibility that time, as we experience it, may be nothing more than a grand cosmic deception. Time feels inescapable. It permeates our lives, from alarm clocks jolting us awake to the relentless countdown to birthdays and deadlines. We measure our existence in seconds, minutes, and years, accepting this flow of time as an absolute, unyielding force. For centuries, this intuitive understanding of time was reinforced by the ideas of Sir Isaac Newton. He envisioned the universe as a vast stage with time serving as a universal clock, ticking away at the same steady rate for everyone and everything. But then came Albert Einstein, and our understanding of time was forever shattered. Einstein's theory of relativity revealed that time isn't a rigid constant, but a flexible participant in the cosmic dance. It bends, stretches, and warps depending on how fast you're moving and the strength of gravity's embrace. Imagine two identical clocks, one placed on Earth, the other aboard a spaceship hurtling near the speed of light. Bizarrely, if you could compare them, the clock on the spaceship would be ticking slower than the one on Earth. This mind-bending concept is time dilation. The faster you travel through space, the slower you travel through time. This isn't some abstract theory. It has real consequences. Imagine twins separated at birth. One stays on Earth, the other becomes an astronaut who spends years traveling at immense speeds. Upon their reunion, the spacefaring twin would have aged less than their Earth-bound sibling. Time would have literally passed slower for them due to the effects of time dilation. Time dilation may seem like science fiction, but it's a fact of our universe that engineers have to account for. GPS satellites, orbiting high above Earth and traveling at significant speeds, experience time slightly slower than we do on the ground. Their onboard clocks have to be adjusted to stay in sync, ensuring the maps on your phone remain accurate. Einstein's revolutionary theories upended our understanding of time. Suddenly, time wasn't a steady constant, but a dynamic player in the cosmic drama. This scientific upheaval sparked a resurgence in philosophical debates about the very nature of time. If time dilation and warped space-time are real, how do we reconcile these concepts with our everyday experience of time's constant flow? Let's explore some of the profound questions that emerge at the intersection of physics and philosophy. One central debate centers on the existence of the past and future. Presentists argue that only the present moment has any real existence. The past is a collection of memories, the future a realm of possibilities. Eternalists take the opposite stance, viewing all of the time, past, present, and future, as equally real and unchanging, like a vast unfurling tapestry. The growing block universe model attempts to bridge these two views. It posits a fixed past, an open future constantly branching into possibilities. and a continuously expanding present moment as our experience unfolds. These seemingly abstract philosophical debates have profound implications. If only the present exists, how can we learn from the past or plan for the future? If the future is already set, does that negate free will? The way we conceptualize time shapes how we understand our place in the universe and the choices we make within it. Perhaps the most unsettling implication of the block universe is the challenge it poses to free will. If the future already exists, laid out like a vast network of paths, are our choices truly our own? Or are we merely tracing a predetermined route? Our sense of agency nothing more than an illusion? This paradox forces us to grapple with the question of what it means to have control over our destiny within a universe where all moments may already be written. Can the block universe coexist with genuine free will? Some philosophers argue that even if our actions are fixed within a timeless expanse, we still experience the act of choosing and the consequences of those choices. Others suggest that true freedom might lie in accepting the predetermined nature of existence and finding meaning within that framework. Why does time seem to relentlessly march forward, never backward? Physicists and philosophers grapple with different arrows of time, each offering clues to the irreversible nature of events. The thermodynamic arrow is one of the most well-known. It stems from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. This explains why eggs break but never unbreak, and why ice melts but doesn't spontaneously refreeze. These irreversible processes give us our sense of time moving in one direction. But thermodynamics isn't the whole story. Our minds create a powerful psychological arrow of time. We vividly remember the past, yet the future remains a mystery. Even the universe itself provides a cosmological arrow, as it continues to expand outward since the Big Bang. These diverse arrows raise a perplexing question. Is the flow of time a fundamental property of the universe, or a byproduct of how we experience the relentless unfolding of change? The bizarre realm of quantum mechanics throws a wrench into our traditional understanding of time and space. Consider the phenomena of entanglement, where two particles become linked in a profound way. Imagine a pair of gloves, one for your left hand, the other for your right. If those gloves are separated and placed in boxes on opposite sides of the planet, they remain intrinsically connected. If you open one box and find a right-handed glove, you instantaneously know, faster than any signal could travel, that the other box contains the left-handed glove. In the quantum realm, particles can become similarly entangled, their properties inextricably linked. Measuring one instantly affects the other, even across vast distances, seemingly faster than the speed of light allows. This paradox hints at a universe where connections might exist outside our usual understanding of linear time. Theories like loop quantum gravity go even further, suggesting space-time itself isn't a smooth continuum, but made up of tiny, indivisible chunks like the threads of a cosmic tapestry. If true, time might not be a fundamental force, but rather an emergent property of this deeper structure, a byproduct of the way these fundamental building blocks interact. These mind-bending theories force us to question the very nature of reality. Could it be that our experience of time's relentless flow is an illusion, born from our limited perspective within a universe that may operate on principles beyond our current comprehension? Perhaps the past, present, and future we perceive are merely convenient ways for our minds to organize the chaotic dance of existence. The true nature of time remains one of the universe's greatest enigmas. Is it a fundamental force woven into the fabric of existence, guiding the destinies of planets and particles alike? Or is it a grand illusion? A convenient fiction created by our own limited perspective? Scientific discoveries and philosophical paradoxes hint at the possibility that our experience of time's flow may be profoundly different from the true reality of the cosmos. If time doesn't exist as we perceive it, what does that mean for free will and our place within the grand story of the universe? Are the past, present, and future simply emergent constructs in a reality governed by laws beyond our current grasp? We may never possess the definitive answers to these questions, but the very act of pondering them reveals the profound beauty and endless mystery of existence. While the relentless march of the clock and the turning of the calendar may shape our daily lives, perhaps true freedom lies in embracing the timeless wonder of a universe that continually defies our understanding. Surely you've heard by now that black holes can be so massive that they can outshine entire galaxies? But some of them are quite mobile, so much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints. Frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the ball cluster closest to Earth. What he discovered was nothing short of groundbreaking: a black hole with a mass about 800 times the mass of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But black holes of intermediate mass turned out to be a missing link, mysterious relatives about which everyone has heard but no one has met. An equally interesting question is how these black holes of intermediate mass form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,855 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light years away from Earth. But what does that proximity mean in the context of black holes? And why is this proximity important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the ejection of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. The main task of Gaia is to map the Milky Way in unprecedented detail, and it was thanks to this painstaking work that Gaia BH1 was discovered. As the closest known black hole to Earth, Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments will be able to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue? And how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole. Located 5,000 light-years away from Earth, this black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 miles per second. The key to this revolutionary discovery lies in a phenomena predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star. This creates a brief brightening phenomena, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. And this is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling. Its speed is about 28 miles per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower, and if it's too small, it catches up due to the abundance of gas and dust in the galaxy. So some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops, and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young, gas-rich galaxies serve as the birthplace of various black hole phenomena. Whether they're luminous black holes or intermediate mass, wandering black holes hurtling through space, or the nearest black holes to Earth, their origins can often be traced back to these bright, young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now, let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, in 2015 opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that reveal a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond or linear pond, the throw of a stone creates an isolated ripple. In a stormy sea, or nonlinear, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merge to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal. Imagine a particle so elusive that trillions pass through you every second but leave no trace. A particle born in the fiery hearts of stars, in the cataclysmic collapse of supernovae, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space, carrying secrets that could rewrite the laws of physics. But why are they so hard to detect? And what secrets can they reveal if we finally learn to listen to their whispers? Diving into the realm of these ghostly particles, we go where the known meets the unknown, and where the smallest particles hold the key to the biggest questions. The neutrino story begins in the early 1930s, when the study of particle physics was undergoing a revolutionary transformation. It was a time when the universe was revealing its secrets to those who dared to explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem. In beta decay, a type of radioactive decay observed in atomic nuclei, energy seemed to disappear. This disappearance contradicted the principle of conservation of energy, one of the most fundamental laws of physics. Pauli proposed a radical idea. What if the missing energy was carried away by an undetectable particle? He tentatively named this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with the already discovered neutron. Fermi, an Italian physicist, was in turn instrumental in developing a theory describing this elusive particle and cementing its place in the scientific lexicon. Let's travel back to the Cold War era, a time when science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the center of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not just about military might. It extended to the realm of science, where both sides sought breakthroughs that could give them an advantage. One such story is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been heavily involved in neutrino research, and his defection caused a stir in both intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era and the extent to which neutrino research had become the subject of international intrigue. This period was marked by secret experiments, some conducted deep underground in abandoned mines or remote locations, where scientists were trying to catch these ghostly particles. Neutrinos, while among the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that for a long time it was thought to be zero. Unlike other fundamental particles, neutrinos interact only through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it were not there. Trillions are passing through you right now, completely undetected. 3 types or flavors of neutrinos are known: electron, muon, and tau neutrinos. Each is associated with a corresponding charged particle: electron, muon, and tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery because it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can move between these mass states, resulting in a change in flavor. This discovery not only won the 2015 Nobel Prize in Physics, but also pointed out gaps in the standard model, changing our understanding of fundamental physics. Neutrinos are also key players in some of the most dramatic processes in the universe. At the heart of a star, nuclear reactions generate huge numbers of neutrinos, which then leave the star almost instantaneously, taking energy with them. Neutrinos are the first particles to fly out of a dying star, signaling the start of a supernova. These particles provide crucial information about the processes taking place in the core, long before the light can escape. When a massive star reaches the end of its life cycle, its core collapses, leading to a supernova explosion. During this cataclysmic explosion, an enormous number of neutrinos are produced, orders of magnitude greater than the energy emitted by light. These neutrinos leave the supernova almost instantly, spreading through space, and some of them eventually reach Earth, giving a glimpse into these distant, violent events. There's also speculation that neutrinos may be linked to one of astrophysics' biggest mysteries: dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino, that does not interact with any known fundamental force other than gravity, may make up dark matter, the invisible mass that makes up most of the universe's matter. Although this remains an area of intense research, the possibility that neutrinos could unlock the secrets of dark matter emphasizes their importance to our quest to understand the cosmos. So the hunt for high-energy neutrinos has taken scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica stands the Ice Cube Neutrino Observatory, scanning the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events that are still cloaked in mystery. Recent research has begun to peel back the layers of this mystery, pointing to active galactic nuclei, or AGNs, as significant sources of these high-energy neutrinos. AGNs are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases huge amounts of energy, often forming jets of high-speed particles. However, recent discoveries show that these jets may not be the only source of neutrinos. In 2022, the galaxy NGC 1068 was identified as a likely source of high-energy neutrinos, a discovery that surprised many in the scientific community. The neutrinos were traced to the galaxy's core, where a supermassive black hole is hidden behind thick layers of dust and gas. This discovery disproved the popular belief that such neutrinos can only be emitted by galaxies with bright jets, such as blazars. The surprises didn't end with NGC 1068. Further studies revealed 2 more galaxies, NGC 4151 and NGC 3079 as potential sources of high-energy neutrinos, the findings strongly suggest that the environment around supermassive black holes and these active galaxies is a powerful neutrino factory. These findings have led to a paradigm shift in our understanding of where high-energy neutrinos come from. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors. IceCube has already made remarkable discoveries, but other projects are on the horizon that aim to push the boundaries of our knowledge even further. In Japan, the Hyper Kamiokande is poised to become a leader in neutrino detection. This huge underground detector, located in a cave specially dug for the purpose, will be filled with 260,000 tons of ultraviolet water. The goal is to capture fleeting flashes of Cherenkov radiation produced when neutrinos interact with water molecules, a technique honed over decades of Japanese research. Meanwhile, in the US, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will utilize a state-of-the-art time projection camera in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map neutrino properties in great detail. Although both the Hyper Kamiokande and DUNE share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K is based on proven technologies and aims at mass data collection. DUNE, on the other hand, relies on innovative technologies that can reveal new aspects of neutrino behavior. The stakes are high. Both projects seek to answer fundamental questions about the universe, such as the origin of matter itself. One of the key areas of research will be a phenomenon known as charge parity violation, which may explain why the universe is composed mainly of matter rather than antimatter. Charge parity violation, CP violation, could be the key to solving this cosmic mystery, and Hyper-K and DUNE are designed to find it. By comparing the oscillations of neutrinos and their antimatter, antineutrinos, as they pass through space, these detectors can show whether there's a fundamental difference in the behavior of matter and antimatter. But the race to find CP violation is also a race against time. Hyper Kamiokande is expected to begin collecting data as early as 2027, which could give it an edge over DUNE, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for decades to come. The Standard Model of particle physics has long been considered one of the most successful theories in science, providing a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations, and nowhere is this more apparent than in the study of neutrinos. These elusive particles, which have almost no interaction with other matter, have properties that push the boundaries of our understanding. One of the most serious challenges to the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to be massless, but the observation of neutrino oscillation, when neutrinos change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model. But that was not all. The consequences of the appearance of neutrino mass go beyond a simple revision of the model. They suggest the possible existence of a new type of neutrino, the sterile neutrino. Now, we've already mentioned this in passing, but here's the gist of it. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos interact only through gravity. This makes them even more difficult to detect, but their existence may well explain several mysteries in physics. If sterile neutrinos are shown to exist, they'd not only call into question the completeness of the Standard Model, but would open the door to entirely new physics. This would require extending the model to include these new particles, potentially leading to a more unified theory of the fundamental forces. Neutrinos may also provide clues to another profound mystery. the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. But today we observe a universe in which matter predominates and antimatter is rare. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter, antineutrinos, may behave differently. If neutrinos do break this symmetry, this could later explain why there is more matter than antimatter left after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence for CP violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a 185-mile, 300-kilometer journey across Japan to the Super Kamiokande detector. For nearly a decade, researchers have noticed that neutrinos oscillate into different types more often than antineutrinos, suggesting that they may indeed behave differently. This potential CP violation in neutrinos could be the missing piece to explain why the universe is made up mostly of matter. However, the current results, while promising, are not yet conclusive. The level of statistical significance required to recognize a discovery in particle physics is 5 sigma. The T2K results have only reached about 3 sigma, and this means that although the evidence is strong, it's not absolute. To truly confirm the CP violation in neutrinos and unlock the secrets of antimatter rarity, scientists are turning to the next generation of neutrino detectors. Hyper-K in Japan and Dune in the US are poised to take this research to the next level. These massive detectors will collect many times more data with greater accuracy, potentially reaching the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science: why there is something rather than nothing. The study of neutrinos, once considered an obscure branch of physics, may ultimately hold the key to understanding the very fabric of our reality. To answer some of physics' deepest questions, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or CATRIN, in Germany. The CATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the tiny neutrino mass. By analyzing the energy of the electrons emitted in this decay, CATRIN aims to set an upper limit on the neutrino mass, pushing the boundaries of discernibility. CATRIN has already made significant progress, setting an upper limit on the neutrino mass of 0.8 electron volts with sensitivity down to 0.2 electron volts. However, this may not be sufficient to determine the true neutrino mass, which may be even smaller. This realization has sparked a global effort to develop alternative methods and experiments that could surpass the capabilities of CATRIN. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays via electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a minuscule amount of heat that can be detected by extremely sensitive equipment. Experiments with holmium-163 have already demonstrated highly accurate energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the Project 8 experiment, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could surpass the limit set by cosmological studies and provide crucial data on the true mass of neutrinos. The quest to understand neutrinos is not confined to one country or continent. It's truly a global endeavor. The challenges posed by these elusive particles have brought together scientists from around the world, fostering collaboration across borders. as we await the first signals from Japan's Hyper-K, which is already taking shape in a newly dug cave, and await news from Dune, nestled deep in an old South Dakota gold mine. The next chapter in our understanding of the universe is just beginning. Stay tuned as we journey through the frontiers of science, making one discovery at a time.